Okay, we were today the integral from 0 to 2 x over e to the x minus 1 dx. I think maybe I did a problem really similar to this. I probably did it from 0 to infinity. I'm going to have to check. I'm kind of curious. Now, what I'm thinking on this one is it's actually quite a bit more complicated than it looks. I didn't try different methods. I was thinking, I don't know, maybe integration by parts would be nice. What I wanted to do is use geometric series, just noticing it's pretty much set up if we kind of think of it as having like a 1 over here. In order to get it where it's going to converge though, I need to multiply in e minus x over e minus x. So then when you distribute that in, what's going to happen? Now we're going 0 to 2. Let's bring the x out front, and then we're going to have something like e minus x. This e minus x times e to the x is just 1, and then we'll have minus e minus x dx. Now for geometric series, we have the formula. We have if the sum is from n equals 0 to infinity of x to the n, this is going to be the same thing as 1 over 1 minus x, as long as the absolute value of x is less than 1 in order to get our convergence. But because we have e to the minus x in the numerator over here, I want a different form. I want to start, instead of starting at 0, I want to start this at 1. And when you do that, what's going to happen here is this is going to be an x in the numerator. So for what we have here in the integral, all I want to do is input e minus x into this formula. So what we're going to have is we want the sum from 1 to infinity of now e minus x in here, but I'll distribute in the n and we'll write it as e minus xn. And so this is going to be the same thing as e minus x over 1 minus e minus x. And for our convergence, we want this now, but this is going to be no problem from 0 to 2. This is going to be decreasing in less than 1. So what that's going to allow me to do is we'll take this and we'll plug it back into our integral. So we're going from 0 to 2, but let's distribute this x in here. So now we have our sum, and this is going to be x e minus nx from 1 to infinity. But because we've established absolute convergence right here, that's going to allow me to swap the order of the integral with the sum. And that way, this right here, this is an integral that's going to be pretty easy for us to do. I can use integration by parts on it. I could use a Laplace transform on it, but I've done that a few times recently, so I just want to mix it up. But that's also a good method, is trying to force this into a Laplace transform. So what I'll do is we'll use the DI method over here to the right. I'll differentiate x and integrate e minus nx. Let's differentiate this all the way down to 0. So when I differentiate x, we get 1. Do it again, we get a 0. Integrate over here, we get e minus nx, but we're going to get a minus n pop out. So we'll have it like this. But then do it again, the minuses are going to cancel out, and we get e minus nx over n squared. So then because of this 0, the integral is going to get zeroed out in the last row, and so we can just kind of put down our solution on the diagonal. So we have, this is still all within the sum. We have some stuff in common. We've got basically, we have this in common in both. So let's factor that out. We'll have it as minus e minus nx over n. And then what's left is going to be just x plus 1 over n. And we still need to evaluate this from 0 to 2. I think I'll take this minus sign and bring it in front of the sum just so it doesn't bother us. And so first let's evaluate at 2. So this is going to become e minus 2n over n. And then plug in here, we're going to have 2 plus 1 over n. Then for the next part, evaluating at 0, you plug a 0 in here, this just becomes 1 over n. And then here, that gets zeroed out. And so we're going to have like 0 plus 1 over n. Let's just write it as 1 over n. And then from here, I think what I want to do is just distribute everything out, breaking it up on the plus and minus. So I think what's going to happen is we're going to end up with 3 sums. We're going to have this piece, and this piece. So like for this first one here, I'm going to have the minus out front. I'll bring the 2 out front, and we'll have the sum. I'm going to write it a little bit differently. Let's break it up like e minus 2 to the n over n. And then for the next one, we need to bring in this 1 over n. So this is going to be minus. We're going to have the sum. We'll write it the same way, e minus 2 to the n. Here, n times n, this is going to give me an n squared here. For this last one, minus times minus is going to be a plus. Multiplying this together, we're going to have just 1 over n squared. And now let me just clean up the board, and let's try to calculate what is this whole sum going to be? Let's see if we can simplify this. Okay, now in order to evaluate this, we'll just take each of these sums separately. And I have a bunch of formulas over here to the right that we're going to be able to use on this. So for this first one, notice this is kind of like, it's basically in this form right here. Our power series for natural log 1 minus x is going to be this sum over here to the right. Well, this is the same as this if we just consider our input, our x value, to be e minus 2, or 1 over e squared. Well, we already have the minus sign out front. It's just 2 times this. So this is going to be 2 times the natural log of 1 minus input this x value, which is e minus 2. I can write this as 1 over e squared. We'll come back and simplify in a minute. And then for this second sum, this is in the right form for the dilogarithm, this one right here. Again, the input on it, our x value, is just going to be the same thing, 1 over e squared. So for this piece, it's going to be just minus dilogarithm of 1 over e squared. And then for this last one, you may just recognize this as the Basel problem. It's also in the right form for the Riemann zeta function. The s value on it's just going to be this exponent, so in our case 2, but the value for the Riemann zeta function at 2 is just pi squared over 6. So we'll plug this in, pi squared over 6, and now I'm just going to look for some simplification. What we can do on this, for 1 minus 1 over e squared, we can get a common denominator, write it as e squared over e squared, like this, and then simplify it to e squared minus 1 over e squared. But this thing's inside the natural log, so splitting it up with log properties, we can have it as natural log e squared minus 1 minus natural log e squared. Take the 2 over here. Natural log of e is just 1. So this whole thing, this part right here, is going to reduce to natural log e squared minus 1 minus 2. So let's take this and just plug it back in to finish it off. Distributing in the 2, so what we're left with is going to be 2 natural log e squared minus 1, 2 times minus 2, minus 4, minus dilogarithm 1 over e squared, plus pi squared over 6, and that's it. So for a simple looking problem, I actually thought that was pretty good that we were able to get the Basel problem, Riemann zeta function, the dilogarithm, and the power series for natural log 1 minus x all into the same problem out of a very simple integral. So, okay, that's it for today. Thanks everyone for watching. Have a good day.